My name is Francesco Nori. I come from the Fondazione Instituto Italiano di Tecnologia and I work for the Robotics Brain and Cognitive Science Department. And today I will talk about complete force control in under-actuated but constrained mechanical system. This is the state of the art in humanoid robot. The current situation sees the robot being able to enter a disaster scenario like the one proposed in the Darpa challenge that you see here represented, being able to open several doors, but as you see, the robot is not able to do it efficiently in terms of time, and it takes more or less half an hour to enter 3 doors. So we're really behind the capability of humans in terms of motor control. So in this video what you can see is actually a human doing extremely advanced motor control movements, capable of jumping and exploiting the passive dynamics in the system in order to perform extreme parkour movements like the one you see here. This is well beyond the current capabilities of humans, and in my research group we are trying to understand how to get these kind of behaviors in a humanoid robot. What is important in my research studies is to exploit the dynamics of the system. There are movements that cannot be described simply by the kinematics or the movement of the system, but you need to exploit the dynamics and therefore the forces that interact and make the system move. In particular, we are interested in exploiting the passive dynamics of the system to get a better performances in terms of efficiency. At the same time, dynamics can give you robustness and be able to replicate the same movement while taking into account possible differences between the model of the system that you have and the real system that you are controlling. And dynamics really matter in the sense that if you see in this video, you can do really advanced movements by exploiting, for example, in this case, the weight of the robot and then the power in the actuators themselves. In order to exploit movements and to exploit the dynamics of the movement, we need to insert control. And in our view, control is a way to obtain a system which is stable against disturbances and which is able to perform the movements that I was describing before. And within this context, contact forces are fundamental. In this picture you see how kids are able to control their posture by interacting with the environment at different locations in their body. It's not just that they are controlling certain position of their hands or feet, but they are exploiting the entire body to interact with the environment. And at the current state of the art, humanoid robots are not capable of doing such advanced maneuver and such advanced motor skills. So within a European project called COTICO, we are investigating how we can transfer actions involving multiple contacts and whole body motion into humanoid robots. Like in this case, when we want to reach for something distant, we are exploiting not just the contact location at the foot, but also using hand to achieve additional support, and then to integrate these skills also with reaching capabilities. And within the project, we are exploring how to transfer this technology and this kind of approaches into a humanoid robot. Along the same line, what we are trying to do is to develop and to transfer motor control skills on several robots within another European project which is called Croibot, where we are using different robots, including the iCub, to understand how a robot could traverse a path composed of different kind of terrains, which currently are very difficult to be handled by humanoids. In particular, the idea is to be able to walk on soft terrain, walking on, for example, a beam like this one, or even to walk over a stair and to place footholds in very specific positioning, and then maybe being able also to enter a scenario where there's a stair here and the door, and the idea is to be able to do it quite efficiently, exploiting the dynamic of the system. And in order to do so, we want to build for real the system. And in particular, we want to be able to develop our own robot in such a way that the modification that we will introduce in the robot will be functional to the goal achievement in the task itself. In order to do so, we have built recently the iCub humanoid, which is a humanoid that currently is used in more or less 20 labs around Europe, and also has been recently used in Japan and Korea and the United States. Thanks to different European projects, the robot was developed, and each time a new skill was added. So the added value of this platform is that the way it's developed is incremental, and every time we develop new skills. One of the most crucial characteristics of the robot was developed within a project which is called RoboSkin, represented here, which gave the iCub a whole body distributed tactile sensor which is covering most of the body. Just to give you an idea what the platform is, I have a video here where you see the capabilities of the robot itself. The robot has two cameras as LED to represent facial expression. This is to perform human-robot interaction. The two eyes have two cameras, as I was saying. The body is covered with this tactile skin, which is used to interact with the environment. The hands are highly dexterous, so there are 9 motors for controlling each hand. You see the two cameras here. And it's also capable of controlling his own hand towards the target. In this case, it will bring his own hand on the ball, and as you see, is now looking at the ball, and then it will perform a reaching action on the object itself. The robot is open source. It's distributed with an open source license, and the idea is to have a platform to collaborate among different laboratories in Europe. And one of the peculiarities is also that the robot is capable of controlling the interactions forces with the environment. As you see in this video, before actually reaching and grasping an object, the robot is feeling the presence of the object by feeling the forces of interaction with the object itself. As I was saying, a peculiar sensor is the flexible skin, which is basically inherited from the technology that we have nowadays available in most of our cell phones. It's a capacitive sensor. The only difference is that this specific sensor developed for the iCub is flexible in a wide sense. So it can be conformed on multiple surfaces, and in particular it has been conformed to all the covers of the robot. So practically 80% of the robot body is covered with this tactile element. It allows the robot to feel the environment and to explore the environment and to control the interaction forces with the environment itself. So this is a picture of the skin itself. As you see, at the moment is covering most of the upper body, and recently we also covered the foot and the legs of the robot. But as I said, we're interested in building and doing things on real robots. And if you consider the application of the ideas that I was describing before on a real robot, you have strict requirements that come up only whenever you want to build things for real. In particular, in the kind of problem I'm considering, computations play a crucial role, so we need to be able to perform computation quite efficiently. And at the same time, we need to have special control capabilities, in particular being able to control the torque at the joints of the robot. And this requires special hardware and special theoretical frameworks. The theoretical frameworks I'm interested in is the ability to control interaction forces across the entire body. And in particular, the approach that I was recently proposing is called task space inverse dynamics. The idea is to control the dynamic equation that describes the system, which is this second order differential equation, by applying suitable torques to perform whole body motion. The system I'm considering is like the one depicted in this picture here, where you have that the robot is first of all free to move, so it's not attached to the ground in any point. So he's able to move his own legs in order to move forward. But also the system is putting his own hands and feet on specific points of the environment. And these create contacts with the environment that we represent in the dynamic equation with a certain number of constraints. So that's why we are interested in controlling this kind of system, so a mechanical system constrained at certain locations. And within this framework, I come to some equation here. It's interesting to notice that, first of all, the system to be controlled can be seen as a linear system. Indeed, if you take all the relevant variables to the control problem that I was describing before, the acceleration at the joint, the force at the contact location, and the torques at the joint, and you assume that you can measure the position of the system and the velocity of the system, then what you get is a system that you can write in the linear form here. So y is the vector of control variables, but the constraints on the system can be expressed in this nonlinear equation where you assume that the position of the system and the velocity of the system is known. And a task for the system, the dynamical system, can be described in the following form. So as a quadratic cost on the difference between a desired value for a certain task variable and a linear combination of the control variable y that I was introducing just a minute ago. The problem can be solved by means of multiple tasks. So, for example, whenever we want to do a whole body motion, we might have a number of tasks like balancing or reaching at the same time. And we are interested in controlling all these tasks and to define across the tasks a certain number of hierarchical structures that define which tasks are more relevant than others. And this is exactly what is represented here in this slide. So in particular, the tasks have a priority level which is determined by the subindex I here, and the lower the index, the higher the priority is. We want to execute the task in such a way that when we execute a task at the hierarchical level I, all the tasks with minor priority will be always kept at their minimum value. What it turns out in this framework is that the control variables can be divided into two sets. So the degrees of freedom are n plus 6 in general. Well, n is the number of degrees of freedom, number of joints in the system, and 6 is the number of free variables of the free floating base. Those n plus 6 degrees of freedom can be divided into motion variables and force variables. Here divided in n plus 6 minus k and k dimensionality. The constraints, which are represented here by the k vector, can be represented as a one-to-one mapping between forces and constraints, because each constraint is also determining a force of the constraint itself. And the n control variables are acting either exclusively on the motion control or can be moved from motion to forces, but they always cover a number of variables which is less than the total number of degrees of freedom. The framework we propose is sort of competing with many other frameworks in literature. What it turns out is that the task space inverse dynamics is optimal, efficient, allows force control, and allows the control of under-actuated systems, which is a peculiar characteristic of the framework we propose with respect to the previous state of the art. In particular, I will discuss a little bit the problem that I was describing before, neglecting more simple problems which can be considered as a sub situation or a simpler situation with respect to the problem I will consider here. So most of the literature in the past have been focusing on controlling motion as opposed to controlling forces. So in this first part of the talk, I will mainly concentrate on the previous framework, which we are considering how to control the motion of the forces, the motion of the system, while neglecting some forces acting on the system. this is just a brief description of, in terms of equations, a brief description of what was the previous state of the art. So again, this is the dynamical system that describes this system behavior. These are the constraints. And in this first version of the equation, you have the contact forces explicitly written here with the force F. So in order to control the system posture, what you can do is first of all compute the contact forces and then to replace these contact forces in the dynamic equation. This is exactly what is described in this equation here. I will be brief on this. You take the expression of the contact forces, which are due to the contact constraints here, and then you plug them back in the equation so that you get an equation which does not depend anymore on the contact forces here. So this expression here, which is called the constraint dynamics, which contains the dynamically consistent nullspace projection matrix NC bar, can be used to compute the torques that realize a certain acceleration Q double dot. And the expression is written down here. Very simple strategy can be improved by a different strategy, which is doing the same computations but more efficiently from the computational point of view. And this is just represented here, where you see that the computational efficiency is determined by the recursive equation, which allows us to build the nullspace projector from one task to the other, and eventually to compute an acceleration, a virtual acceleration, that will be used in the control action here to compute the torques that realize the desired motion task. And this is kind of important. This control strategy does not need contact forces, and in particular does not need to measure contact forces to be implemented. As opposed to this strategy, we have investigated a different control strategy, which consists in using the control variables to control all interaction forces and partly the motion variables, while leaving out certain motion variables. And we proved that the zero dynamics of this motion is actually stable, so that it's well posed to control forces, neglecting a certain part of the motion variables. The description of the system is again quite similar to what we've seen before. So we have a certain number of tasks that we want to execute, which are indicated here with JI. And these tasks can be either a motion task, X double dot I, or a force task, F star I. And again, what we do is a sequence of tasks in a hierarchical structure. So the hierarchy is represented here with tasks with higher priority, which will be executed tasks with minor priority that will be executed with within the null space of the task with higher priority. Again, here is just the solution of the problem that I just described. The final control solution, I don't enter into the details, but it's just a recursive null projection which takes into account the priority of tasks, and the higher priority function, the higher priority task is the one on controlling the interaction forces, and is represented here with this hybrid dynamic representation of the solution. The framework can be used to control the total position of the robot, and in particular, the Newton-Euler equations can be used to control the center of mass position and the angular momentum of the system. So by controlling the interaction force, we can control the so-called centroidal dynamics, which is represented here, by selecting the forces F in such a way that we can give a desired velocity to the momentum of the system, which is represented here. Of course, there is an ambiguity in the way of selecting interaction forces F, and this ambiguity can be solved with a minimum strategy, with an optimal strategy, by minimizing a certain quantity, in this case the difference between the desired force and undesired reference force F0. In order to perform the task, it's also very important to have a very precise torque control capability, and in order to do so we have set it up an experimental phase that allows us to improve the motor transfer function identification. So in this slide it's just a brief description of what we do in order to get this description of the torque dynamics. There's a first phase where we identify the so-called constant torque constant of the motor, which is the proportionality scalar which relates torques with voltages given to the motor. In the second phase, what we do is identifying the viscous coefficient of the system by assuming that the motor constant torque is known, and then moving the system trying to identify what is the friction acting on the system. This is just a video, shows the identification procedure. So the robot will be initially maintaining a given position, and the experimenter will apply to the robot a certain external torque. So you see the robot is position controlled, and the person here is applying a certain external force, and during this phase we identify the value of the torque constant k tau, represented here as the proportionality between torque at the joint and voltage applied to the motor. In the second phase, instead, the robot starts moving, and during this phase, by measuring the velocity of the system, a different constant is identified, and in particular, in this case, the viscous friction constant is identified online. Okay. So what about the implementation on a real robot? And this will be the end of the talk. We implemented this control strategy on the robot to maintain balance. So in this video, the robot is balancing by controlling the force at the contact point. In this specific case, the contact will be at the right foot and the left foot. So the robot is standing on his own foot. It's controlling the forces on the 2 feet, while at the same time controlling the posture according to a certain impedance with respect to a reference configuration. So the robot is trying to maintain the initial posture, and whenever an external force is applied, it's behaving like a spring, in a spring-like behavior, while maintaining the balance thanks to the force at the contact point on the left and right foot. The guys start being kind of rude with the system, but still the robot is able to maintain his own balance. In the second case, the robot is doing a different action. In particular, is trying to move the center of mass of his own body from the left foot to the right foot continuously. So you see the robot is swinging left and right. And again, this is done by controlling the forces on the right and on the left foot, doing what we call complete force control. And at the same time, he is maintaining a posture which is a reference posture, which is maintained with a certain impedance around the configuration of the robot. So whenever an external torque is applied, the robot reacts by behaving like in a spring-like behavior and trying to bring back the body to a reference configuration, as you see here. Okay, that's the conclusion. Happy birthday to the International Journal of Advanced Robotic Systems.